Yes, my name is Kizito Ryan from Group 25, where we will be tackling the problem of real-time spatial-temporal action recognition for burglary and vandalism detection via deep convolutional architecture. In the course of this presentation, I will be looking at those different subtopics. To start with, burglary is unauthorized breaking, or you would say entry, into a place with intention to commit theft. Vandalism, on the other hand, is just intentional damage to property. In traditional surveillance, CCTV cameras are combined with human monitoring, and some of the problems with that are fatigue, intermittent attention, and delayed response, which leads to a high rate error. Our solution makes use of computer vision to see and understand video content automatically. It also applies action recognition to detect and classify human activities in the video. This is due to spatial temporal modeling to analyze both the space to know what the objects are, plus the time or motion patterns using deep learning, where we will be applying convolutional architecture. Yes. And on top of that, we will be applying real-time detection, which is instant analysis that still makes use of live cameras. These are some of the related works we were able to look at. One of the papers by Sultani, where he talks about a C3D combined with a multiple instance learning architecture. And those were some of the key results of that model. An OAK of 75.41. Some of the limitations of this model were heavy 3D CNN and high compute, making it inappropriate for surveillance edge hardware. The result is it is weak on fine-grained anomalies, and it has no location generalization. There was an i3D baseline 2020 to 2022 as a second study we were able to look at, which makes use of an inflated 3D component. Those were the accuracies that were outlined on violence datasets. It had a very high memory and latency, making it poor for real-time performance on edge devices. The third was wood, and this made use of a convolutional neural network combined with long short-term memory to give an accuracy of 68 to 71%. It has a limited long-range dependency model, which struggles with severe class imbalance. We had Tran that made use of a video transformer with a very high accuracy on action datasets, but it has a very extremely high computational cost, and it is not optimized for surveillance edge hardware where you would want to deploy the model. We had a hybrid CNN transformer 2023 that made use of a ResNet architecture that is combined with a transformer encoder, giving an accuracy of 72.5% and an F1 score of 0.69, which was a moderate compute, but it had a limited evaluation on held out locations. And what we are proposing is a ResNet 18 backbone CNN combined with a lightweight transformer. And in our training and study, it was able to achieve a 73.91 accuracy in percentage and a macro F1 of 0.713, giving a burglary OAK of 0.761. This was both a lightweight and edge-friendly architecture suitable for surveillance edge hardware deployment. It was very strong on imbalance, plus location robustness. Which brings us to the problem statement. Our domain will be smart security and surveillance systems. And the problem we're tackling is manual monitoring of those systems that is inefficient, unreliable, and also at times not time efficient. The need is to automate real-time detection of both burglary and vandalism. The goal is to improve response time and enhance the public and private sector security. The computational problem is that you have to analyze the video automatically, extract the features from the video frames, classify the activities going on in the video, and perform burglary or vandalism detection. Some of the questions we asked ourselves were, how will that data be prepared for training? How can the model detect burglary and vandalism? How accurate is a model in detecting suspicious activity? And some of the objectives we were able to come up with in that quest were to collect and evaluate, pre-process the video data set, to develop a burglary and vandalism detection model, to train it as well, deploy the model for real-time surveillance, and implement the system. We developed Some of our contributions were that we developed a burglary and vandalism detection model, built it for future extraction, trained and evaluated that model, and implemented a real-time surveillance system. We worked under a strict architecture, as you can see in the diagram, where you will have your edge device as a surveillance device, where the model will be deployed. But the pre-processing, the frame extraction, temporal segmentation will go on in the brain, not of the camera, in the brain where the model will be deployed. And that model will have access to a knowledge base, or what you would call weights of the classes, against which it can judge as it is analyzing the video, pull out the scene context, have a normality analysis, and then that information will be sent to an actuator or a decision engine to do a confidence assessment, and then finally lock down a trigger and then give you feedback on what is going on in the scene. We were able to try 8 different architectures, and all of them use a similar pipeline, but are differentiated by the way input is optimized before it is preprocessed, how spatial and temporal learning are handled, but all to give classified output. To begin with, we had a hybrid CNN plus transformer, and this takes in the input video, extracts frames from it, and these frames are passed through the CNN backbone to extract features from each of the frames to generate a feature sequence that is then passed to the transformer encoder that carries on with the temporal learning. And the results of that are passed through a fully connected layer so that the information can be classified to give an output of the classes. In the second model was the C3D, where it takes in still the video output, but this time it does not extract frames to extract a sequence from each of them, but rather it takes the 16 frames and combines them into an input frame video that is passed through the convolution layers, and 3D Max pooling is done on them to generate the temporal instance, and this is passed through the fully connected layers to classify the models, thereby giving output. The third was the inflated 3D that takes in an input video clip. It cuts out a short clip from the video. It takes that in. It is passed through still the ResNet 18 backbone. It makes use of a ResNet 18 backbone. Global average pooling is applied on that input video clip, and the final classification layer will tell you which class it is. The fourth was the autoencoder and classifier model that takes in an input video, uses an encoder for spatial and temporal feature extraction. And for this particular model, both spatial and temporal extraction are treated with the same weight to give a latent representation that is then decoded and sent to the classifier, which will give you the output class. The fifth was the convolutionary LSTM model, and this takes in video input still, and the number of frames are extracted from the video, and features will be extracted from each of these frames to generate a sequence of features that is sent to be processed by the long short-term memory that will then generate a representation that is passed through the fully connected classification layer to give you the predicted results. The sixth was the two-stream CNN, which still takes in video input, and the similar frame extraction is done just like in the CNN plus LSTM. But then in this two-stream CNN, after frame extraction is done, 2 concurrent streams are used to analyze the data. That is the spatial stream that deals with what is taking place in the frame, and the temporal stream that is supposed to deal with. The spatial stream deals with what exists in the frame, which are the object representation, and the temporal stream that deals with motion detection or what is taking place in the stream. And after this, that 2 future vectors generated are then concatenated and sent to the fully connected layer where they will be classified and the predicted results generated. The seventh was the convolutionary long short-term memory architecture, which still takes in video input. Features are extracted from the video and sent to the convolutionary LSTM layer, where the memory mechanism that generates a representation that is sent to the memory mechanism, and then a final representation of that is sent to the fully connected layer to give you the output. The last was the transfer learning architecture that still makes use of the 3D ResNet 18, and this takes in video input, and a number of frames are extracted from the video, which are then encoded spatially and temporally encoded to be passed through a pre-trained 3D CNN backbone, where they go through the 3D convolutions to be sent to the residual blocks, and then onto the global pooling to give you a final representation that is passed through the classification layer to give softmax output. In our dataset, we used a video-based surveillance dataset organized into 3 behavioral classes, which are burglary, vandalism, and the normal class, as talked about in one of the slides earlier. The dataset is structured into class-specific folders, with each of the folders containing multiple video clips recorded under varying lighting conditions. During exploratory data analysis, we examined the following aspects, which were class distribution and balance, video duration and frame count variations, FPS and resolution consistency, motion intensity patterns, brightness and scene characteristics, potential dataset bias for features like lighting, environment, and camera position. And some of the extracted visualizations we had were, for example, we had a class distribution, which helped us identify a very high class imbalance, which triggered us to do class weighting and reduce on the size of the normal class. We had duration versus files, a duration versus file size scatter plot that generically showed that there were very few outliers, and that duration and file size would not be a very important factor to consider in our training. We had a duration distribution per class scatter plot still, and it showed that the normal classes tend to be a bit longer than the rest of the burglary and vandalism video data. We still had a frame count versus duration scatter plot, and just like the duration versus file size, it indicated that there were very few outliers, but most of the data lied within the same frame range. We had a motion comparison box plot that showed that burglary videos tend to have a high intensity in motion, followed by normal data videos, and vandalism having the lowest motion score. We had a resolution distribution, and this was even for all the data. A duration histogram, it showed that most of the videos lied within the same range of duration. A video with distribution box plot histogram that showed that all the videos had a uniform width, same for the height distribution, showing a uniform height for all the videos. An FPS distribution that showed that all the videos lied within the same range of frame count. And we had a feature correlation heat map as well. We had a motion score distribution. On top of that, we had a motion versus duration scatter plot. We had a motion distribution, a violin box plot, a brightness distribution across the 3 classes that showed that the normal class had the lowest brightness distribution. We did an RGB channel distribution, having 3 box plots as shown down there. We're able to do an edge density comparison, motion over time, KBE, average duration per class, and average motion per class. After training the 3 classes, we were able to weigh them against a series of metrics, of accuracy metrics, and one of them was the test accuracy, or the accuracy they attained on test data, the precision, the recall, macro F1 score, and the key ROC value that was given in the order of the 3 classes: burglary, vandalism, and normal. The hybrid was able to score the highest test accuracy. It also scored the highest precision. It came second best in recall, and also had the highest macro F1 score. When it came to the ROC where that is the ROC values that are able to tell us how best the model can differentiate a class from the rest of the classes, it scored a 0.761, which was 4th best for burglary. It scored a 0.681, which was 4th best for vandalism, and a 0.826, which was 4th best still for normal. We still chose this model because of its lightweight transformer that makes it very suitable for edge deployment on the edge devices we are targeting to use after deployment of the model, which takes us model selection and deployment, the hybrid and transformer CNN. And this is the pipeline we followed to deploy it. We created a repository for the model, Hugging Face, uploaded both the model and its class labels to that repository, and then we created a gradual space where we would be building the application and the application under which the model will work as a brain. In this application, we were able to build an application Python script and the necessary requirements file, and the two are linked. The model repository and the Hugging Face space were linked, and through this we were able to generate a live demo of the application that can give predicted results. These are a few snippets from the real-time deployed application that can be accessed via that link, where it allows you to both use a live camera and also upload already pre-stored video data. And after that data is uploaded, you can just click on Analyze Video, and then it will display the detection results in the right panel. The class with the highest percentage after being displayed on the detection results is the predicted class. We also performed a model compression where we applied two methods, and in the first method, we combined knowledge distillation with quantization. And for the knowledge distillation, we trained a lightweight student model to learn from the originally deployed model using its truth labels and output probability distributions. This distilled model was further quantized, or what you would say, we reduced on the computational accuracy of the model after it had been distilled from a 32-bit to an 8-bit integer without retraining it. And through this, we were able to reduce the model size from 132 megabytes after distillation to 4.2 megabytes as a student model, which was then further reduced to a 4.1 megabytes after quantization. The test accuracy remained slightly the same. And the second method, we used weight pruning plus quantization, where in weight pruning, you reduce on the number of filters that are applied across the training process. And this reduces the computational overhead of the model, thereby making it lighter. And we were able to then still combine this with quantization to reduce on the computational accuracy of the model, thus further reducing, which further reduces the size of the model. And this was able to reduce the model size from 139 MBs to 11.86 MBs. And the test accuracy was slightly maintained by reducing by just a 5% from 73.9 to 68.2. Concerning model compression, in conclusion, the int8 model from the first method that combined knowledge distillation and quantization was chosen and deployed as a lighter version of our first hybrid CNN and transformer due to its higher retained test accuracy and its smaller size. We have included a link below there so that you can access the actual live demo where that model was also deployed. Some of the limitations we faced were lighting and scene bias, because there are very many variations in brightness and color, indicating environmental bias that may affect generalization of the model as it is learning. We were able to apply brightness, normalization, and data augmentation to improve the model's robustness. The other issue was feature overlap between classes. For example, motion and visual features partially overlap across most of the classes. So the combination of convolutional neural networks and long short-term memory would have been a good, with class weighting, would be important to capture the subtotal behavioral differences and reduce the number of false positives per prediction. In conclusion, we realized that motion is not a strong behavioral indicator because both burglary and vandalism videos consistently showed higher and more dynamic motion patterns compared to normal footage, confirming that temporal modeling is really essential rather than just spatial modeling. Structural features alone are insufficient. Things like duration, file size, and resolution differences that we were able to identify during our exploratory data analysis do not clearly separate the classes, meaning the model must learn complex spatial temporal patterns rather than simple structural features. Below are some of the references that we used in our study while carrying out this project. I'd like to acknowledge our supervisor for providing the necessary supervision during the project. We would also like to acknowledge the university that has provided the necessary resources to aid this project. And below is the web. We would also like to acknowledge the website where we were able to get the video data that we used in the training of the model. Thank you.